Welcome to AP Calculus, Lesson 1.4. This is 1.4a, Limits of Trigonometric Functions, Analytic Approach. At this point, most of our limits are going to be analytic. And these first two limits, we'll see that we can use what we learned in 1.2, which is direct substitution, because these functions are defined and continuous at theta for these given thetas. So for instance here, theta approaches 2 pi over 3. I always check my denominator first. Check my denominator. So this would be sine 3 over 3 times, where theta is 2 pi over 3. And I look at my denominator, my 3's cancel here. And I have sine of, 3's cancel here as well, 2 pi over 2 pi. 2 pi is defined, so I don't have a situation with this function not being defined. The denominator does not equal 0. I can find sine of 2 pi by going around to 2 pi, and this point is 1, 0, cosine sine. Sine of 2 pi is 0, so I have 0 over 2 pi. This is okay. 0 on the top is always all right. It just means I get 0. We have a similar situation with this function where I'm taking the limit as theta approaches pi. There isn't even a fraction here, and cosine is continuous on its own, so I can just substitute this in to cosine theta equals pi. And when I have this square here, this means that it's the entire cosine that is squared. 2 cosine of pi will be over here, -1, 0. That's cosine and sine. So cosine of pi is -1, and that -1 is squared. 2 times 1 equals 2. So in each of these cases, I find that these functions are defined at the value that I'm taking theta to, and so I can use direct substitution, it's no problem. However, I will have some situations where the function is not defined at the value I have theta approaching. We're going to look at one such example right here. When I try my direct substitution, always checking my denominator first, I find that I get sine of 0, quantity squared, and sine of 0, here is 0, 1, 0, cosine sine, sine is 0. So I would end up with 0 squared in the denominator, which is undefined. So I can't take this limit by direct substitution, but just because direct substitution yields something that is not defined does not mean that the limit does not exist. That's a cop-out if you just try to give up. We always have to look at some other way to solve the problem. Our first approach that we want to try is rewriting our trig functions in other terms to see if we can cancel something out. And here we have this sine squared theta, which should make us think, okay, this might use our Pythagorean theorem of trig, which is sine squared theta plus cosine squared theta equals 1. We want to substitute out sine squared theta, so that means I want to get sine squared theta by itself. Sine squared theta equals 1 minus cosine squared theta. So I can rearrange this function to get sine squared theta, and I can substitute what it equals in here. So now my limit is the limit as theta approaches 0 of 1 minus cosine theta over 1 minus cosine squared theta. So I'm getting closer, but I can't actually cancel this. I can't cancel the 1's. I could check my direct substitution and see, can I plug this in? But I'd get 1 minus, and cosine of 0 is 1. 1 minus 1 squared is still 0. So I can't do this here. But 1 is a perfect square, and cosine squared is a perfect square. So I can factor this difference of squares. Still the limit as theta approaches 0 My numerator, I'm not making any changes right now. My denominator I can rewrite as 1 plus cosine theta times 1 minus cosine theta. And now I see that this will allow me to cancel my 1 minus cosine thetas. This gives me a limit as theta approaches 0 of 1 over 1 plus cosine theta. So now I can try this direct substitution. Cosine of 0 is 1, so I get 1 over 1 plus 1 equals 1/2. And this is now my answer. So this, by expressing my trig functions in terms of other trig functions, allowed me to cancel out something from the denominator so that I now have a definable function. It's a slightly different function than what I started with, but the limit is still the same because when I'm taking limits, I can cancel things out and it's still the same limit. Let's see a few examples of these. If you're following this in class, these are ones that you can either do with the homework and check your answer, or you can save to work during class. If you decide to save them to work during class, you can skip ahead to the next section now. And I suggest, if not, that you go ahead and try these yourself and then come back and check to see how you did. I'll post the answers in a moment. Right, you can see the answers at the bottom here. Let's look at each one of these. This is theta. As theta approaches 3 pi over 2, I'm going to go ahead and set up, here's where 3 pi over 2 is, and this point is 0, -1, cosine sine, so that I can quickly grab those values when I need them. And my problem here is tangent of 3 pi over 2 is undefined. That's a vertical line. It's sine over cosine, -1 over 0. So I need to somehow get rid of part of this tangent. I'm going to start by expressing tangent as sine over cosine. So I have 3 sine theta over cosine theta times cosine theta, remembering that my tangent here became my sine over cosine. This now lets me cancel my cosines, because the cosine being in the denominator, that's what's causing me the problem, this right here. Once I cancel my cosines, now I have the limit as theta approaches 3 pi over 2 of 3 sine theta. And sine of 3 pi over 2 is -1. So 3 times -1 equals -3. For number 2, this is at pi over 2. I'm going to go ahead and mark my pi over 2. This is the coordinate. I go over 0 and I go up 1, cosine and sine. So secant of pi over 2 is the reciprocal of cosine. That would be 1 over 0, and that's undefined. I can't use that. So I know that secant is something that I want to try to cancel or change. And I'm going to start by just, I have two approaches here. I could rewrite this as 1 over cosine. It's reciprocal identity. So I'd have the limit as theta equals, as theta approaches pi over 2 of 1 over cosine theta times cosine theta over 4 theta. And that clearly allows me to cancel my cosines. Another approach is that if you become familiar with it, you can just know that secant times cosine, anything times its reciprocal, just equals 1. Either way, that lets me simplify this function as theta approaches pi over 2. Now my limit is 1 over 4 theta. I don't actually even need to look at this circle here because I'm not being asked to find any trig anymore. This is just going to be 1 over 4 times pi over 2. 4 and 2 cancel and leave me 1 over 2 pi. Number 3, this is as theta approaches pi. I'm going to draw my pi. Coordinates are -1 over, 0 up, cosine sine. And I see here that sine of 0 equals 0, which would give me a 0 in the denominator. So it's this sine that I need to try to cancel out. I'm going to go ahead and rewrite tangent as sine over cosine. which gives me the limit as theta approaches pi of cosine theta times sine theta over sine theta times cosine theta. This one's lovely. Cosines cancel, sines cancel, and that gives me the limit as theta approaches pi of 1. Anything divided by itself is 1. Now what is 1 as theta approaches pi? Well, if you have an apple, what happens to it when all strawberries become cherries? You still have an apple. So this just equals 1. As is mentioned here, it's important to note that you should always try direct substitution first. Many times direct substitution will work. Then if direct substitution doesn't work, you're going to want to do one of 3 things. We already covered one, and that is simplify sines, cosines, tangents, secants, cosecants. Try to put everything in terms of sine and cosine so that you can reduce things. However, with this example here, sine theta over theta, there's nothing really for us to simplify or reduce. But what we can do is actually find a special rule. This is our sine theta over theta rule that we can use to simplify anything that in a more generalized form is sine c theta over c theta. In other words, this c could be any number as long as the top and bottom, top on the inside matches, outside as the coefficient of theta matches. We're going to find the special rule we can use. And we're going to find this is the limit for the limit as theta approaches 0. Obviously, that would make this undefined. It would make the function undefined. But my limit still exists, and I could see that if I were to plug in the values here. And I'm just going to write them in real quick so that we can observe the results. All right, so here we can see what our values would be in our graphing calculator. And as we approach 0, which would lie here, as theta approaches 0, as we approach it from the left, getting close to 0, looking at our y values, we can even see at 0.01, we're getting very close, and then closer to 1. We are approaching 1 from the left. And I might not even have exactly the right number of 9s here. It's a lot of 9s. So we're getting extremely close to 1. And as we approach from the right, towards 0, we also find with our y values, we're getting closer and closer and closer to 1. So we could say the limit of sine theta over theta equals 1. From the left we approach 1, from the right we approach 1, so the two-sided limit equals 1. Here we can see something similar. You can fill this chart in yourself with your graphing calculator. I'm going to leave that one to you, but you should find as a result that from the left, sine 3 theta over 3 theta also approaches 1, and from the right will approach 1. Therefore, our two-sided limit, we converge toward the same value of 1 on both sides. And that's because this 3 and this 3, they match. The one inside the sine function, it always has to be a sine function. The one inside the sine function and the one that's the coefficient of theta match here and here. Based on what we've observed, then, what inference can we make about the value of the limit of sine c theta over c theta, where c is any constant? That could be 3, 2, -1, anything. We find that the limit as theta approaches 0 of sine c theta over c theta equals 1. It always equals 1. Now here we have a slightly different function. This one is 1 minus cosine theta over theta. And we want to find, again, as theta approaches 0, because that's what would make this undefined. Take a moment and fill these boxes in with your calculator. Pause, evaluate, fill them in, and then we will read together what they approach. Okay, you should have these filled in now. We're going to approach 0 from the left. We're going to approach 0 from the left, and as we approach our y value, our function, y minus cosine theta over theta, from the left, we're going to find that we also approach 0. And the same thing as we approach 0 from the right. As we read our y values, we're going to find those also approach 0. 0, there we go. And therefore, my two-sided limit, as I approach from the left and I approach from the right, I converge toward the same value of 0. This gives us two special limits that we can use. The limit as theta approaches 0. The first is our sine rule, and you'll need to eventually memorize these. But our sine rule is sine of any constant times theta over that constant times theta. And these also apply in their reciprocal form. So I would get this equals 1, or c theta over sine c theta would also equal 1. Then I also have my cosine rule, the limit as theta approaches 0 of 1 minus cosine c theta over c theta. But this one equals 0. So my sine rule equals 1 and my cosine rule equals 0. In 1.4b, we will work several problems like these so that we can see what they look like in action.